Welcome to CS 340. I'm Frank. This is your very attractively dressed co-host. Today we're going to talk about boosting for a little bit, mostly so you have a sense of what's out there, and then we're going to move on to probabilistic reasoning at the level of CS 340. Okay, so we talked about ensembling methods earlier. Today's a pretty easy lecture. It's a bunch of stuff that you actually don't need to learn because it's all in tan. And then some stuff that you do need to learn, but it's pretty brief today. So we talked about ensembling before, and in your midterm, even you ensemble classifiers, you ensemble a classifier via a stacking method. Ensembling methods are also called meta-learning. They have really interesting, ensembling classifiers have really interesting names: averaging, bootstrapping, bagging, cascading, random forest stacking, so on and so forth. And the idea is, of course, that ensembling methods often have higher accuracy than the input classifiers, input models, right? So we're going to talk about a different way of ensembling today, basically boosting, but the fundamental trade-off still applies, right? How small can you make the training error? That's E-train, and how well does the training error approximate the test error? That's the approximation error, approximation, E-approximation. The goal of ensembling is to build a meta classifier that does much better on one of them than the individual classifier or any individual classifier, but it doesn't do too much worse on the other. And as before, this suggests averaging. We also did stacking in the midterm, right? So averaging improves the approximation error of classifiers with high approximation error, right? In other words, basically deep classifiers that it might overfit, you might want to average them in order to make a better ensemble. But today we're gonna highlight the existence of boosting, which is a way of improving training errors of classifiers with high E-train, which is to say weak learners that have relatively large training error, that if you sort of stick them together in particular ways, you can make an ensemble of classifiers that works much better. And basically, up until the probabilistic reasoning portion of this lecture, basically all the boosting stuff is in tan. You should know about it, and we want to point you to some resources that you can look at to go deeper if you want to. Yeah, the first method we'll talk about is AdaBoost, which is sort of a classic boosting method. You should be aware of its existence. It's sort of like the perceptron algorithm. It's that fundamental in the history of machine learning. And then we'll talk about XGBoost, which is sort of a modern boosting algorithm that does very, very well in many practical settings. And you should be aware of it if you're going to go off and actually do machine learning, because you want to use this for solving your Kaggle competitions and that sort of thing. So a classic boosting algorithm for binary classification, like, classic as in, like Shakespeare kind of classical, is AdaBoost. Although Rob probably wouldn't like it if I said that. Basically, AdaBoost assumes that we have a base binary classifier that's simple enough that it doesn't overfit too much. Think decision stump or something like that. And it can obtain 50% weighted accuracy on any data set. Okay, so the idea is you have your estimate. Let me change color. You have your estimate, the true label, and then there's a weight associated to those. So long as you can actually achieve better than 50% weighted accuracy on any data set where, the equality shows that example I is classified correctly and the weight sum to 1, then you can boost such a classifier through the AdaBoost training procedure to produce very, very high accuracy classifiers. So an example of such a weak or base binary classifier as a decision stump or low depth decision tree. And it's pretty straightforward if you think about it for a second, how to modify, stumps or trees to use weighted accuracy as the score that you're trying to optimize. So what AdaBoost does is it fits a classifier in the training data, and then it gives a higher weight to examples that the classifier gets wrong. then it refits a new classifier, a new classifier on the weighted training data, and then you go back to 2. Okay, so basically you get weights get multiplicatively or exponentially larger every time you're wrong. And the final prediction is a weighted vote of the individual classifier predictions, where the trees with higher weighted accuracy get higher weight. Okay, and the derivation for AdaBoost is extremely tedious. You can look it up on Wikipedia. It's not that hard, but it's long and tedious. And we're going to basically move away from AdaBoost with XGBoost anyway. So you want to be aware of AdaBoost and be pointed at the right research to understand what's going on. So if we look at a 2D example of AdaBoost with decision stumps, with accuracy as the score that you use to decide splits. Over here, so what do we have? So this look here, this is going to be the weak learner, the stump, the base classifier that gets selected at every step of the AdaBoost algorithm. Over here is going to be the ensemble classification boundary. And over here, if you look at individual data points, particularly in this region, I assume that you can see what's going on here. The exponentially growing or multiplicatively growing weights will appear as the size of the data. So we consider, okay. So we had an ensemble of 1, right, which was the original decision surfaces shown here. The ensemble has a particular error, and data points that it got wrong got upweighted, right? Okay. Then another decision stump was inserted, which basically goes there. Okay. And the weighted classifier that comes out of AdaBoost learns a decision surface like this, where now you're getting these wrong and these wrong, and these wrong. So these are going to get upweighted at some point, and these wrong, so on and so forth. Now we learn another decision stump, which is a different split along this axis, presumably to deal with these data points right here, right? And so on and so forth. And this repeats. While this is going, I should be able to remove my pen markings. I'm starting to get sophisticated. So it's really struggling to bend this curve over here. Okay, so this is basically what AdaBoost does as you're learning an increasing number of decision stumps, and you can see that the complexity of the decision surface grows over time, basically. Okay. But all you ever have is you have basically a collection of these decision stumps that then you vote amongst. So the ensemble is a collection of these decision stumps that are weighted appropriately according to the algorithm, such that the final decision boundary looks like what you see over here. Okay, and the particulars of AdaBoost, we don't go into them. We're not going to go into them. We're not going to drive it out. It's, again, rather tedious. You can look it up on Wikipedia, but you should be aware of its existence for sure. Okay. So that was a 2D example of AdaBoost with decision stumps, split using accuracy score. It achieves 100% training accuracy on this particular data set using an ensemble of 50 decision stumps. The point is these are fit sequentially, not independently. So it's not like a forest like we were doing before, where you do bootstrapping and bagging and all that sort of stuff. We're going to fit these sequentially. Our decision stump's a good base classifier. You can argue about this. They tend not to overfit, obviously. You can get 50% weighted accuracy. There are some base classifiers that don't work in general. If you use too strong of a base classifier, then there's no errors to boost, basically. So like if you fit the data right away in the very first instance, then there's no boosting gain to be had. The nice thing is that the AdaBoost boosted classifiers learn better decision surfaces that generalize better, basically. Okay, so AdaBoost with shallow decision trees gives fast and accurate classifiers. And classically, this is the important part, it was viewed as one of the best off-the-shelf classifiers. And the procedure originally came from ideas in learning theory. There's lots of stuff in the literature about going beyond the binary case, and there are modern boosting methods that look like AdaBoost, but don't necessarily have it as a special case, like they don't reduce to AdaBoost. XGBoost is one of those. Another, we're still, tan colored here, right? But you should know about XGBoost. It's a modern boosting algorithm, and it's maybe, I think it's easier to sort of explain heuristically what's going on or intuitively what's going on. So XGBoost is a boosting classifier regressor that you can use to fit huge data sets, and it's been used to win a bunch of Kaggle competitions. Sorry. As a base classifier, XGBoost uses regularized regression trees. Okay. Oh, sorry, I see there's a question. Today, random forest is the best off-the-shelf classifier. Yeah, that would be true. I would say there's a strong argument that canonical correlation forests are, but nobody knows what they are yet. So that's another story. Anyway, XGBoost is right up there. XGBoost didn't exist at the time of the paper that was written that chose classifiers. So it would be an interesting empirical study to compare XGBoost and canonical correlation forest and random forest, so on and so forth. XGBoost is powerful. So how does it work? Here's our data. We've got a bunch of individuals. We have features for all of them: age, occupancy, city, so on and so forth. A regression tree is built where the split is based on one feature, so it's a lot like one of the random one of the decision trees we were looking at earlier in the course. And every leaf, though, here gives a real valued prediction. Okay. Right. So if you have a 14-year-old kid who owns an Xbox and you're trying to predict how long they're going to spend playing video games, they're going to get filtered down over here. If you have an oldie or a set of oldies like me, you're going to get filtered down over here. And now the question is, how do you compute this quantity, right? It's fairly straightforward when you're doing just regression. You can just take the average, basically. So how do we fit it? Well, the simple approach is to predict at each leaf. You just predict the mean of the training data assigned to the leaf. So you shove all your training data down through this tree. And this is just the mean of the data assigned to the leaf. Okay, so these weights here are the model parameters, and it's important in future slides to recognize that the weight WL at leaf L is a parameter, and it's set to the mean of the data among the data at that leaf node. Okay, and to train the tree, you set the weights or the parameters values by minimizing the squared error. Cool. Yeah, so Li is the leaf into which Yi descends, and that's pretty much it. Okay, so fitting this has the same computational cost as fitting individual decision trees from week 2. You use the mean function instead of the mode function at the leaves, and you use squared error as the split criteria instead of accuracy or info gain or Gini index or something like that. Like you just check whether or not taking a particular split on a particular feature gives you a reduction in squared error. Okay. And you use the same kind of greedy strategy. You just choose the split criteria and value that greedily optimizes the loss. Okay. So how do you do prediction? Well, so we have an ensemble of regression trees. For every example I, they make a continuous prediction. So like Yi might in this tree get filtered down here, it might get filtered here in this tree, it might get filtered through here in this tree and filtered in this tree. And each one of these is going to produce, because of the weight at that particular leaf node, a real valued prediction for that input point. Okay. But what's different about XGBoost is that the prediction is the sum of the individual predictions. Okay. It's not the average, it's the sum. Okay. Okay. So that's different than what we did with random forests. And what this reflects is the fact that in boosting, we're doing something very different. Actually, we're learning the tree not to predict the true yi. Each tree is not doing that, but basically what we're going to show is that what you do is you learn this tree to make the prediction, and then you learn this tree to correct for the mistakes that this tree made. Okay, so you fit the residual of the prediction made by this tree with this tree, and then you fit the residual made by these two trees of the prediction made by these two trees using the third tree, so on and so forth. Okay, so each new tree tries to fix the prediction made by the old trees so that their sum is yi. Okay, so here's a gradient tree boosting procedure. So fit the first tree using the full data and the labels, right? Y hat, you make a prediction then using the first tree and the input data X. Yeah. The second tree you fit using the input data X and the residual, right? And then your second predictor, this could be 1, this could be 2, something like that, right? Is formed by predicting using the first tree and then adding the prediction of the second tree, and so on and so forth. Okay. So each tree is trained to predict the residuals of the current prediction, right? The true label is 0.9, the old prediction was 0.8, so I can improve y hat I by predicting 0.1, okay? Okay, so if you have an input feature X like so, and values associated to each individual value of xi, basically your function looks like this blue curve from input to output. If we fit a low capacity tree, right, to this with a decision surface, like with a decision rule that splits on X at this value, and for instance, you have a leaf here and a leaf here, is the values that come out, then the residual in this region is 0, and the residual over here is not 0. Okay, so if we subtract the prediction from the true label, then the residual is here, and we use this as the function that we try to fit using the second tree. Okay, fine. The prediction then is the sum of the both trees, which in this particular case would fit the data exactly because the residual in this entire region is also 0. Okay. So we can watch gradient boosting in action. Here's one of the regression stumps that we talked about. Clearly there's a split in the X value here, right? So this is, down below. Down here is X, over here is Y. Second stump comes along, and you'll notice that this second stump, the function that it learns, does not look at all like the actual function, but instead it looks like a function that deals with the error that was made over here in the original, by the original stump. And by adding these two together, you get an ensemble that looks like this, right? And if you continue this process for a long time, and I'll clear my pen markings. You see that it learns. Can we use boosting and stacking? Oh, now you can take XGBoost and you can stack XGBoost with other things, and you can ensemble and you can stack and you can average, and yeah, you can do all of these things. Yeah. And this is, part of model selection, right? Now you have an exponentially large space of just boosting and stacking, right? Will it make me unstoppable? It will make your code unstoppable in the sense that it will run forever, probably. But yeah, I mean, probably better off trying to actually find the real relationship between input and output if you can. Okay. So long as the weights or the parameters, basically the leaf parameters, are not all 0, adding a tree will decrease the training error. So obviously XGBoost type models can overfit if the trees are too deep or if you have too many trees. So one way, basically regularization comes into XGBoost in kind of an interesting way. To restrict depth, you can add an L0 regularization penalty on the weights themselves, just like we did before, right? So basically, in order to split, in order to actually add a new leaf anywhere, right, you have to actually decrease the ensemble error by lambda naught. And in order to further fight overfitting, you can actually downweight or try to shrink the parameters W, as we always do. Okay, so this is what the XGBoost objective looks like. So, what is XGBoost doing? Instead of pruning trees, the score doesn't improve. It grows full trees and then prunes parts away that don't improve the score with the L0 regularizer that we just talked about. The cost of fitting trees in XGBoost is the same as the usual decision tree cost, but the actual code and implementation for XGBoost has lots and lots of tricks to make this efficient. The critical part is that you can't fit the trees in XGBoost in parallel like you do in a random forest, because we're sequentially fitting the residuals. So there's a sequential fitting procedure, so it's a little bit longer. And the relationship between XGBoost and AdaBoost is that the residuals in XGBoost act like the weights in AdaBoost. And something to think about, if you decide to use a different loss than the squared error, where you can solve for the mean basically directly, if you're using some sort of non-quadratic loss like a logistic regression, then every time you decide to split or actually set a model parameter at one of the leaves, you have to solve an optimization problem. So it's a non-trivial thing to generalize beyond the squared error. And again, you can read the XGBoost paper if you want to get this. That one way to do this is to approximate the non-quadratic losses with second order Taylor expansions, and then you get least squares efficiency for actually setting the weights in individual leaves at some loss in precision. It doesn't really matter. Okay, now we finally get to the fun part of the course for me: probabilistic thinking. Oh, thank God, we're here finally, and we only get to do a couple of lectures on it. But any questions at this point? Otherwise, I'll just.
I have a question about the boosting. Isn't it too sensitive to outliers basically? Because every time you want to try to fix the error, right? So if there's outliers, how do we deal with that?
I think the question of outliers is a little bit orthogonal to boosting, right? In the sense that every model is sensitive to outliers in some sense, right?
Yeah, for sure.
Are you referring to one of the particular algorithms in particular, or just in general?
Well, in general, in every classifier is obliged to fix the error in the processor, right? So every scale, right? So if there is outlier, then there's going to be a problem, I think.
I would say that's true. That's definitely true for AdaBoost, because of sort of the exponential increase in weights, and Yeah, I would say that's true. In XGBoost, it's not so clear that it's such an issue, because you know the tree can partition off that outlier pretty rapidly, right? But indeed, in AdaBoost, it's a nasty problem. Yeah, and one of the reasons why it's doesn't show up as often now. That's a really good point. Thank you. Okay. So turns out that actually a lot of this stuff, it's kind of like moving on to quantum physics from Newtonian physics, but actually much easier because, well, it's just everything that we've been doing is much easier. Turns out that basically everything that we've been doing can be characterized as maximum likelihood estimation or map estimation. Okay. And we're going to talk a little bit, not as much as I would like to. This is what 440 is about, and eventually I'm going to take over 440 because that's my cup of tea. But the reason to think about probability and maximum likelihood and maximum a posteriori estimation and that sort of stuff is that it's crucial for understanding advanced methods and understanding what's going on actually in general. But the concepts and notation can be a little bit difficult at first, particularly if you don't have a background in statistics. So why do we think about these? When we did counting estimates for probabilities in naive Bayes, we're actually doing maximum likelihood, right? When we decided to minimize a squared loss, we were actually making an explicit distributional assumption about the errors in a regression model. When we decided to move away and do robust regression, we were actually changing the distributional assumption we made about the errors in a regression model. When we did regularization, like adding one, MAP stands for maximum a posteriori. When we talked about Laplace smoothing, basically adding a 1 to the denominator, well, actually that's a form of regularization for maximum likelihood in Bernoulli likelihood models. Why did we use a sigmoid link function to get probabilities and logistical, what were the probabilities for, where do they come from? Well, that's just, MLE with a particular link function and a categorical loss. Or categorical likelihood, excuse me. And basically, if you need to think about writing down loss functions for more complex kind of regression or classification problems, then you really need to think about likelihoods instead of losses, and the likelihoods allow you to think about generating things like number of Facebook likes or ordinal ratings or something like that. And if you're going to go on and actually work on machine learning in research or in research industry research or whatever, then you actually need to understand probabilistic methods and certainly maximum likelihood and MAP. We have been talking a lot about maximizing and minimizing functions. So we've been using the min and max functions a lot, where we say the min with respect to w of w squared is 0, and the max with respect to w of cosine is 1. These give you the minimum or maximum value achieved by a function over its entire domain. A related and perhaps more important set of functions that we really haven't talked about, which is kind of crazy, are the argmin and argmax functions. And these give the sets of parameter values that achieve the maximum or minimum. So the minimum of w minus 1 squared is 0. The argmin of w minus 1 squared is 1. So that's the value of w that minimizes, that gives you a min of the function, right? So the argmin of the squared regularized, squared loss regression problem is the solution to the normal equation. This is the w that minimizes this expression. Okay. The argmax of cosine of w is the set of all even multiples of pi, right? They're all of these points, right? Okay. I will be pretty sloppy when I talk about argmax and argmin, right? I often say, the argmax is when in fact there can be multiple values that achieve the max or min. So the argmax and argmin should technically be thought of and should return sets. So we should say, the argmin of this is the set containing, or so on and so forth. And the language that we should say is, we shouldn't say variable is the argmax. We should say it is in the argmax. But like I'm pretty bad at this. But you should be aware that the argmax and argmin are set valued functions. Okay, cool. That's all it's saying here is that they're in the argmin rather than equal to the argmin. Okay. All right, so suppose we have a data set. In this data set, it's going to be counts, it's going to be whatever, doesn't really matter. These are our observations, and this data set has some parameters and a model. We have a data set and a model, probabilistic model with parameters W. Okay. In fact, we might as well just write this down. So we're going to say P of D given W. This is going to be our likelihood function. And we're going to actually just go ahead and say, well, let's make the ID assumption and say that this is going to be product over I of P di given W. Okay. And we can go one further and remind you that if we have, we flip a coin 3 times and we have obtained some data set, heads, tails. Okay. So the probability that di equals heads equals W. Probability that di equals tails is 1 minus W. Okay, great. Okay, so probability di equal to W indicator di equals tails times 1 minus W. Times 1 minus W indicator di equals, oops, this is going to be heads, di equals tails. Okay, fine. So the likelihood, this thing, we define as a probability mass function, right? So the probability of data, whatever it happens to be, okay? Given the parameters. If D is continuous, then it's probability density function, okay? So if if we're modeling a fair coin, right, meaning that it lands on heads with probability 0.5, then the likelihood of an individual data item, this term right here, will look like this. Okay, in other words, it will be Bernoulli distributed. Okay, and the likelihood, the total data likelihood in a coin flipping situation is just the product of all of the probabilities of the data given the model parameter. Okay, so this is P of flip 1, D1 given W. This is P of D2 given W. This is P of D3 given W, so on and so forth. Just take the product of all of them. And if it's fair, then the probability of heads, tails is just half times half times half, and that's equal to 0.125. Okay. If W is 0, then the probability of heads under this model, let's go, W is 0, well, that would be 0. Then this would be 0, and this would be 1. And we take a product of all of those, is 0. Okay. If W is 0.75, and you go over here and you go over to the right and look what's going on, if you're going to pick off one term of 3/4 from let me give you a, don't I have the ability to, I'm going to pick off 2 terms of 3/4 and 1 term of 1/4 from here. Okay. main point is, you're going to get, 0.75 times 0.75 times 0.25, and this is 0.14. Okay. The main point is that under a Bernoulli likelihood model, the probability of the data given the parameter varies depending on the parameter. So here all we're doing is the data is fixed. It's always heads, heads, tails, but we're moving the parameter around. We're moving the parameter from 0.5 to 0 to 0.5 to 0 to 0.75. And the likelihood of the data is different in these cases. And in fact, you can see that the likelihood of the data is higher if we choose W equals 0.75, because that parameter generates the data with the observed data with higher probability. Okay. So we can look at this vertical axis here is, and this horizontal axis is W. We can plot the total data likelihood function as a function of the parameter, right? And we can think about what does it mean to find the argmax, what's argmax W of P H H T given W. Okay, what is that? Okay, and what does it mean? Well, the argmax is here somewhere, right? And what does it mean? It's the parameter of the model that explains the data the best, that makes the observed data the most likely. Noticeably, the data, this particular data item, this sequence has probability 0 if W is either 0 or 1, because there's both heads and tails in the data. The data doesn't have highest probability at 0.5 because there are actually more heads than there are tails, right? And this is a function, it's a distribution over D, not W. So if you integrate this curve, it does not sum to 1, okay? Because the thing that we're integrating over is on this side of the conditioning bar, not on the other side, okay? Okay. So maximum likelihood estimation is the procedure for choosing parameters that maximize the likelihood function. Okay, exactly as I wrote above. Well, not quite. I wrote W star instead of whatever. Okay, in this particular example, the maximum likelihood estimate is 2/3. Okay. Okay, so how do we do maximum likelihood for binary variables, which is the general case of what we just talked about? So these are heads and tails, so on and so forth. How do we do it for binaries? Well, if we use W, or we say W is the probability of 1, then a TDS derivation will say that a maximum likelihood estimate under a Bernoulli likelihood model of the parameter W is just counting the number of ones over counting the number of examples. Okay, and this estimate for the probabilities that we used in naive Bayes is actually maximum likelihood in a Bernoulli likelihood model. Okay, now, yeah. The conditional probabilities that we use in naive Bayes are the same thing, right? So this is basically saying what's the probability? What's this? You can think of this as being P spam equals true given, Vicodin. This is one of the naive Bayes features. So the conditional probabilities that we estimate in naive Bayes are also maximum likelihood estimates of basically the exact same form. The derivation is really tedious, but if you're, it's online, you can look at it. Yeah, we can go through it if you want to. Anyway, there we are. Pretty good so far. Questions? No questions. That's great. I mean, it means it must be super obvious. Great. Cool. or you already know it, which is even better. So maximum likelihood for fitting probabilistic models. We have a data set D. We want to pick parameters W. Obviously, we have a model as well. Have model. We define the likelihood. That's the part of the model is the probability mass function. We choose the model parameters W hat to maximize the likelihood. Statistics will give you all sorts of really amazing characteristics of maximum likelihood estimators, minimum unbiased variance, all sorts of stuff. We can go through lots and lots of details. I sat in the stats department for many years, could bore you to death with it. The basic idea is that it's a reasonable thing to do if you have a reasonable amount of data and your parameter space is not infinite. For us, it turns out that most of the objectives that we've talked about have a maximum likelihood estimation. In particular, if we consider minimizing the squared error that we've talked about, this is the maximum likelihood estimator for a linear model with IID noise that we assume comes from a normal distribution, which is to say that you can write this down in a whole lot of different ways. Yeah, so I mean, yi distributed normally about W transpose xi with sigma I here, or you can write it down like R equals Wi minus W transpose xi is distributed normal 0 epsilon I. Sorry, that's totally not right. Neither of those are right. That was an idiot, being an idiot. Stop. Go away. No. Okay. Let me do that again. Somebody should have stopped me. So basically, all of these things mean the same thing, and yeah, the idea is like a Gaussian is another name for a normal distribution. Least square solution is called the normal equations. Where do you think that comes from? It comes from this normality assumption about the residual. So in other words, that's a residual, and we assume that the residual is distributed in some kind of a way. Okay, and we'll see this here. Right? So if we have inputs here, X, outputs Y, we have the least square solution in blue, and we have the residuals here. The assumption that we're making is that each one of these epsilon i's is distributed normally with mean 0 and some variance, which in least squares, in the case of least squares, we assume to be 1. Okay. And so to sort of intuitively get an idea of what's going on, if we take all of those errors and histogram them,
least squared isn't good for heterospect.
Oh, good. Okay, we've got some thinkers. This is good. I like it. We've got some active thinkers. So I'm kind of confused. I thought MLE was supposed to be separate from the loss function stuff we've been doing so far, but least squares is an MLE. Okay, so I think we need to clean up the language there just a little bit. So yeah, solving the normal equations it gives you a maximum likelihood estimator in a model in which we make the assumption that the residuals epsilon I are normally distributed. Okay? And we can write this down in 6 ways to Sunday, and I can do it afterwards and when we're summarizing if you would like. So I think the main point is that many of the loss functions that we've looked at have corresponding likelihood functions. So losses, likelihoods, they're kind of the same thing, actually, right? Not quite. Losses are arguably more general. Likelihoods have alternative and arguably more defensible explanations in some cases. So least squares isn't good for heteroscedastic data. Precisely correct. So if you know, for instance, that over here, so if people don't know what, okay, it's a little bit subtle. Okay, so if you know over here that your errors are larger, you can always write yi is distributed normally about, W transpose xi plus some function here of xi. That's totally fine. Or in particular, you can just like say, sigma squared xi, and then write sigma squared xi is equal to something if 2 if xi is greater than 7, and 1 if whatever. Okay, so you can go as far as putting different noise on every single different data point, and you will still do least squares minimization, but you can treat outliers, or so you'll still be minimizing the squared loss, but you can have noise that's input space dependent, if that makes any sense. Hopefully that makes sense to at least remote. Anyway, so to compute the maximum likelihood estimate, we usually equivalently minimize the negative log likelihood. So log likelihood is shorthand for the logarithm of the likelihood. So and it's equivalent to minimize the negative log and to maximize the probability of the data, or the likelihood. They're equivalent because the logarithm is strictly monotonic. So the location of the maximum doesn't change if we take a logarithm, and changing its sign flips max to min. Okay. All right, so we talked about boosting, mostly non-examinable, non-testable, blah, 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 but you should know about AdaBoost and you should know about XGBoost, right? In particular, XGBoost is a modern boosting method that came out of Amazon, basically based on regression trees, and the trees fit the residuals, and there's regularization imposed to keep the model from overfitting, and it works well on a wide variety of data sets. And we just started talking about maximum likelihood estimation, where we're thinking about maximizing the likelihood function given the parameters. And next time, what we'll do is we'll start to talk about where regularization and loss smoothing fits into the maximum likelihood framework. And that will be it for today. Thank you very much. Questions, comments, worries, criticisms? There's a meanie in this class that gave me a bad review on ratemyprofessor.com. I'm like, everybody's getting bad grades now. MAP, maximum a posteriori MAP. MAP, oh, is that supposed to be explain like I'm 5? MAP E, explain like I'm 5 TY? MAP, okay, so we're going to do MAP next time and these sorts of things, but let's do it anyway. So we've been doing D and W. So there is a joint distribution of D and W. Let's have some fun. We've been talking about the likelihood. Then there's a prior. Okay. Great. Okay. So we've been talking about maximizing this guy or gal with respect to W. Okay. We can also write this is P of W given D times P of D. These are just standard rules of probability, right? And because of this, we can write down this okay. So this is of course our favorite Bayes rule, right? Okay. So if you look at this and you try to do arg max w p w given d, and that's arg max w p of d given w p of w. Okay, you don't have to worry about the d. You can put a log in here. That's totally fine, right? And what you're going to see is that when you put a log in here, this is the same as putting a log here, right? And this looks like a log likelihood, which is a loss. And this looks like something else. And that is going to be, this is called a log prior, but it's also called a regularizer. So when you're doing map, you are actually maximizing the posterior probability of parameters given data. And the posteriors is proportional to and related to the likelihood and the prior. And the likelihood shows up as a loss, and the regularizer and the prior shows up as a regularizer. So basically this connection is what connects the machine learning that we've been talking about with probabilistic machine learning. And this problem of estimating the evidence is what makes Bayesian machine learning, which is basically what I work on, hard, very hard. Cool. Yeah. Of course, no problem. Okay, anything else? I don't think so. Thank you very much for your time.